In space, silence is absolute. No voices, no echoes, only the distant murmur of cosmic radiation and solitary particles crossing the void. And yet, within this setting of extreme stillness, a silent but overwhelming revolution is unfolding: the birth of the first quantum computer in Earth's orbit. It is not an experiment for its own sake, nor a mere technological test. It is the beginning of a new era, in which the boundary between theoretical science and practical application dissolves thousands of kilometers above our heads. An era in which quantum computing, until now confined to ultra-cooled, shielded laboratories on Earth, merges with the space race, giving rise to possibilities that only a few years ago belonged to science fiction. When we speak of quantum computing, we speak of machines capable of processing information by exploiting the most counterintuitive and fascinating laws of quantum mechanics: superposition of states, entanglement, the collapse of the wave function. We speak of devices that no longer operate with classical bits, but with qubits, units of information that can exist in multiple states simultaneously. This makes it possible, at least in theory, to tackle computational problems of enormous scale with unprecedented speed. Taking such a system into space is not just an act of engineering audacity. It is a necessity dictated by both practical and scientific reasons. In June 2025, the first operational prototype of a quantum computer left Earth's atmosphere, integrated into a satellite launched into low orbit. The project, the result of collaboration between the University of Vienna and the German Aerospace Center, had a clear goal: to test the behavior of qubits in an environment without gravity, exposed to extreme temperatures and cosmic radiation, far from the electromagnetic disturbances of our planet. The results, still under analysis, promise to open new paths not only in computation but also in fundamental physics. But why take such risks to bring a quantum computer into space? The motivations are many, and some are truly surprising. First of all, space offers conditions that, in a way, can be favorable for qubits. Zero gravity, the low temperatures of orbital shadow zones, and the near-perfect vacuum are all factors that can help stabilize quantum states, reducing decoherence phenomena that on Earth are among the main limitations of these systems. Of course, cosmic radiation is a dangerous enemy. It can interfere with circuits, cause errors, even destroy quantum information. But precisely for this reason, testing the resilience of a quantum computer in space is the first step toward building more robust, reliable systems suitable for future, perhaps interplanetary, missions. Another crucial advantage is tied to latency and efficiency. Today, most satellites capture enormous amounts of data, images, signals, measurements, which are then transmitted to Earth for analysis. This process requires a considerable expenditure of energy, time, and bandwidth. A quantum computer in orbit, capable of processing and filtering data in real time, can drastically reduce the need to send everything to the ground. It can identify patterns, compress information, even make autonomous decisions on which data to keep and which to discard. It is a step toward a network of intelligent satellites, capable not only of observing, but also of understanding the world they monitor. The potential applications are vast and fascinating. A satellite equipped with quantum computing could, for example, improve weather forecasts and environmental monitoring by detecting anomalies in climate data in real time. Or it could manage the logistics of a satellite constellation, autonomously optimizing routes, resources, and tasks. It could even contribute to global security, through ultra-secure quantum communications based on quantum key distribution, QKD, exploiting entangled photons exchanged between Earth and space. And here comes one of the most visionary ideas: the orbital quantum internet. A global infrastructure that allows the sharing of quantum entanglement on a planetary scale, ensuring unbreakable communications, perfect synchronization of atomic clocks, and new protocols for the secure sharing of sensitive data. In this scenario, quantum computers in orbit would no longer be mere calculation tools, but actual nodes of a planetary quantum network, a kind of orbital brain, capable of operating beyond the limits imposed by classical physics. But to achieve all this, a series of technical and physical challenges must be faced, challenges that define the boundary between the possible and the utopian. The first, perhaps the most formidable, is quantum decoherence. Qubits, by their very nature, are fragile. They can maintain their quantum state only for very short times before interaction with the environment. Even the slightest forces them to collapse into a classical state. In orbit, far from terrestrial interference but exposed to cosmic radiation, this problem becomes even more delicate. A single energetic pulse, a charged particle passing through the circuit, can irreparably alter the ongoing computation. It is like trying to write a message on an ice slab during a cosmic sandstorm. To mitigate these risks, researchers are experimenting with new architectures and materials, as well as hybrid strategies. The idea is to combine quantum and classical computation, using the power of qubits only for the most complex tasks, while leaving less sensitive operations to traditional computing. In this way, a synergy can be achieved that not only increases efficiency but also adapts better to the variable conditions of the space environment. It is like having a quantum co-pilot that steps in only at critical moments, while the classical pilot handles routine. Another formidable obstacle is cryogenic cooling. Many types of qubits, such as the superconducting ones used by Google and IBM, require temperatures close to absolute zero, achievable only with complex and bulky cryogenic systems. Bringing them into orbit means miniaturizing them, making them autonomous, making them work in environments where every watt of energy counts. Some researchers are exploring alternative technologies, such as photonic or trapped ion qubits, which can operate at higher temperatures and are potentially more stable. But each of these technologies has its limits, and the compromise between reliability, size, consumption, and computing power is far from resolved. And yet, despite these difficulties, the idea continues to take shape. The Deep Space Quantum Link is a project aiming to connect quantum satellites to create a distributed orbital network. Each node of the network can perform operations, communicate securely, and maintain entanglement with other nodes. In the future, it could even connect Earth with bases on the Moon or Mars, paving the way for an interplanetary quantum system. Beyond practical applications, there is also a profoundly philosophical dimension to all this. Taking quantum computing into space means testing quantum theory in conditions never before experienced. It means exploring what happens to entanglement phenomena in microgravity, or checking whether decoherence behaves differently outside Earth's gravitational field. Some physicists hypothesize that, by observing the behavior of qubits in space, we might obtain clues to a future unified theory between quantum mechanics and general relativity. In other words, these small floating circuits could help us answer fundamental questions about the universe. We stand, therefore, at the dawn of an epochal change. As with nuclear energy or artificial intelligence, quantum computing will bring with it unpredictable revolutions. But unlike its predecessors, it will not be confined to laboratories or the servers of a few companies. It may orbit above our heads, observe the world, interact with planetary systems, even collaborate with artificial intelligences to make autonomous decisions. In this new technological ecosystem, information will no longer travel only between servers and devices, but between entangled qubits separated by thousands of kilometers, between intelligent satellites collaborating in real time, between Earth, Moon, Mars. The next frontier is no longer ultra-fast computing or extreme miniaturization. It is the integration of quantum thought and space. It is the idea that one day, perhaps very soon, humanity's most complex decisions, from managing global climate to data security, from space navigation to the exploration of the universe, will be made by systems that combine artificial intelligence and quantum computing, orbiting around an ever more interconnected planet. At that moment, the silence of space will be broken by a new form of technological consciousness, capable of thinking, analyzing, deciding. Not according to classical rules, but following the mysterious and fascinating logic of quantum physics. And all this, paradoxically, begins with a tiny qubit, fragile yet powerful, silently floating in orbital void. If you have made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes the difference. Until the next exploration.